Hello and welcome back to another video with It's Dr. Dan, and today we're going to be going through the tips and tricks for solving gas law problems. And one thing that you might have realized is that while learning all these gas laws, there are a lot of them, and it's really difficult to try to keep your brain straight when you are trying to solve all these difficult problems. So what we're going to go through in this video is the tips and tricks of how to essentially organize your brain and how to do this. So the very first thing we are going to be doing is while solving these problems is we need to stay organized. Therefore, if you stay organized, you get a good grade, which is exactly what we want in a chemistry course. So when we are staying organized, what are we going to do? Well, we need to write down what our given and our desired terms are in the problem. So when we look at a word problem, we need to go word by word, sentence by sentence, and try to highlight and pick out all the key numbers and terms that are being said in the problem, and look for little clues that are being hinted along the way of it. Now, why is that important? Well, one thing we're trying to do is we need to be able to match those given terms to the formulas that are being given, meaning we've got to try to fit the puzzle pieces together that we are being given. Because one thing you might have realized is that with gas laws, and specifically the chapters going over that, there are close to a dozen formulas that you have come across, and it can be quite overwhelming to figure out which one is the right choice. So we're going to go through that. We're going to look at all those gas laws from my previous videos on gas laws. So if you haven't covered those yet, I would recommend going back to those first before going through these ones because they are tougher examples. All right. So let's take a look at our gas laws and let's go through some different problems with them as well. All right. With the gas laws, there were two major categories of gas laws. So when you first started this, so in my part one video, I talked about Boyle's law, Charles' law, and Gay-Lussac's law. Afterwards, on part two, I talked about Avogadro's and the combined gas law. Now, with all of these, right, there's a lot of formulas that are involved here. So how do you figure out which one to use? Well, the big thing is keeping in mind that we have to be organized, write down our givens. Now, what makes all these formulas similar to one another? What is the big thing? So, especially when we compare these to the ideal gas law, which is a little different. So, what makes these so different? Well, the secret is in the subscripts. So, one thing is that you see here is that there are a bunch of ones and twos written on the screen, and that is telling you that the system or the gases that you're observing are changing. So, being that they are changing, this is giving us a hint of some sort of really big picture. What is increasing? What is decreasing? How's the system compressing? How's it expanding? All these little key words that we need to look at to be able to see how is their change. So if you see a different gas balloon or system or piston or whatever term changing, you're going to be using these. And you're going to notice that because you're going to have multiple pressure values given, multiple volumes, multiple temperatures, multiple moles, right? So you're looking for all those changes. So keep in mind for later. Now, in comparison, the other set of formulas, right? That wasn't all of them. It's like, oh God. There was the ideal gas law, and then there's Dalton's law. Now, for these two, one thing about them is that they don't reference change. These are referring to the current condition of the gas, especially when you're looking at something like the ideal gas law. Notice here that PV is equal to nRT, and there's no subscripts by any of these values. So what is that telling you? It's asking you, what is the current state of your gas? And that's the important thing. Now, with Dalton's law, you can be like, well, Dr. Dan, you just said that there's no subscripts here and there's a bunch here. Well, this is referring to many gases all shoved in the same balloon or same environment that you're in. Think of your room, for example, that you're in. You're breathing air. What is air made out of, right? It's oxygen, what you need to breathe, but you're in a nitrogen rich atmosphere. So there's nitrogen, oxygen, CO2, and all the other aromas and odors that surround you at all times. Those are all the gases. But you can kind of see that the total of each of these is referring to the current situation that you're looking at. So there's a difference. You have current, and then you have how it's going from one state to another. So what we're going to be doing is we're going to be going through these different, some harder problems to try to identify and how I would think about going through these problems. Let's take a look. All right, the first problem is all about being organized. So what is it? Let's take a look. Well, it says if a 10-liter balloon at STP has its pressure increased to 2 atmospheres and its temperature is increased to 300 Kelvin, then what is the new volume? Now, looking at this problem, that is a lot to unpack. So let's take a look at what is here. Well, the first term, what it tells you as we go through the problem, it says a 10-liter balloon. Liter is a volume. So the first thing we want to do is write down our volume, which we have as 10 liters. Now, the next part that it mentions is that, oh, it's at STP. Now, what was that? STP is a standardized temperature and pressure. So it's telling you it's at that current condition, and its condition in this case is referring to what is the standard temperature and pressure. So the standard temperature is 273 Kelvin, and the pressure is 1 atmosphere. So we're going to write that down. Now, the next part says that it has been increased. Okay, there's that key, one of those key words that I was mentioning earlier. The word increase, so we can see that in a couple places in this problem. What that's referring to is that the conditions are changing. So meaning we're going to be using one of our earlier gas laws, right? So one of the ones that we have a condition change. So what it tells you is that the pressure was increased. So, okay, so we're going to have, in this problem, we're going to have P2, which tells you, oh, this is going to 2 atmospheres as a result. So that's going to be changing. Now, it also mentions that the temperature increased to 300 Kelvin. So that also increased. And then it asks you, okay, well, what is your new volume? So being organized, we're writing down all of our values. You need to write them down. That's crucial. So which formula will this match to? So you're going to go through your list and you're looking for, well, which one of these uses 3 variables? And one thing you're going to realize is that your combined gas law, the original version, tells you, okay, here we have all these variables. So we're going to use it and plug our variables in to solve it. Now, I know a lot of students are not the most comfortable with rearranging a math problem, but it does make the math a lot easier if we do that. So how exactly can we rearrange it? Well, first thing is we can we got to get volume by itself on the right-hand side. So the way we can do that is essentially multiply the the right-hand side and the left by the inverse of pieces we don't need, which are pressure and temperature on the right. So we'll do the same thing on the left. Okay. And then as a result, what's going to happen is the pressure is going to cancel. Temperature is also going to cancel. So what that's going to leave us with is the only thing that we essentially care about here is the volume. All right. So we'll have only the volume here. We can kind of move this guy around for ourselves to make it a little bit easier to work with. And we are now going to plug our values into this new formula. So, okay, let's do it. So we have on the left, we have 300 Kelvin, and that's going to be divided by 2 atmospheres. Notice how we're trying to be organized, plug in our different values, and that's going to be multiplied by the original left side, which is your pressure of 1 atmosphere times your volume, which is 10 liters. And we're going to be dividing all of that by 273 Kelvin. And you want to double check yourself that you are putting down all of these values. You want to make sure you don't accidentally leave anything out, just because it is really easy to do so. So once we put that all in our calculator, we can also kind of put all this together if it helps you see that, oh, all this is one big fraction as well, just like this. Boop, boop. We'll just multiply all those little pieces. So if we multiply the top, it's 300 times 1 times 10, and then we're going to divide that by 2 times 273. And when all of that happens, what we will get for volume 2 is 5.49 liters is equal to the second volume. Now, does that make sense? Well, we can look at our values, and if you remember, pressure and temperature increased. And pressure and volume, they are opposites of each other. So if the pressure increases, the volume should decrease as a result. And that was a very substantial change. It was doubled. And you can see the volume is almost halved as a result. Okay, so this is doing the first one. Let's take a look at another. Now, the next important skill for how to solve these gas law or any math problem is how to understand the concept of a constant. So in these formulas, you can see that you have pressures and volumes and temperatures and moles. They're on both sides of the equation. Now, when something is held constant, meaning that it's not changing. So let's say it's 1 atmosphere on the left and it's still 1 atmosphere on the right. Well, that value never changed. So therefore, it can be canceled out. So let's show an example of where that is the case. Now, the good news is if you remember, I showed you that there were about 6 different formulas, all involving subscripts. Now, if you understand the concept of constants, you can use the combined gas law to solve almost every single problem involving change. So, in this problem, I'm going to show you how. So, if we have a glass jar at a constant volume, so keep that in mind, right? So, let's kind of highlight that for ourselves, constant volume with a leaky lid, and it contains 0.27 moles of air. Okay. Now, and this is going to be heated from room temperature to 100 degrees C. So that comment of heating tells you, oh, the temperature is going to go up. Now, it also says that you have a constant pressure. So pressure's not changing. How many moles are left in your jar? Okay, so what formula are we going to use here when this is happening? Let's also kind of list out what we have. So in this problem, we have that N1 is equal to 0.27 moles. We want to know what N2 is. And then we were given 2 temperatures. So we had 22 degrees Celsius, and then T2 was 100 degrees Celsius. Now, the thing is about gas laws, you have to remember what units can temperature be in. It has to be in Kelvin. So let's quick convert these to Kelvin. So quick conversion is add 273 to each of your Celsius numbers. So what we're going to get in terms of Kelvin here, so we'll use a different color, is we have 295 Kelvin for T1, and then T2 is going to be 373 Kelvin. So to do our quick conversion. Now, there is no quite formula that matches this based on what we had before. If you remember from earlier, we had the following different formulas, and none of them talk about pressure and moles together. So, or sorry, not pressure and moles, temperature and moles. You see pressure and temperature, volume and moles, volume and temperature, none of them cover that. So what can we use? Well, the only thing that has both those terms is this combined gas law that has no specific assumptions to it, meaning it's the expanded combined gas law. It has moles in it. It's an extra part. So let's take a look at how we can use that. So we're going to be using this expanded gas law to show how we can take out constants. So in the problem, it told you that pressure and volume are constant, meaning that they're not changing. So there is no, essentially, there's no subscript for pressure and volume. So we can actually kind of delete those. And when we show this problem, well, if they are the same, they're going to cancel each other out. So what we can actually do is instead of putting pressure and volume, it's going to be the equivalent of having a 1 on top because they're going to be the same value. We don't know what the value is, but you know that they're the same because it's constant. So now this formula here isn't quite usable the way it is. What we can do is to make it usable is take the reciprocal or the inverse, meaning flip the fraction to put it in a usable form. So what does that flipped fraction look like? Well, simply get rid of the 1 over T2 and or T1 N1 and T2 N2. We have our new formula, which is just this. We got rid of everything else. You can do this with any problem involving change. You can get rid of the constants. So from that, what do we want to solve for? Well, we want N2 by itself. So we'll divide both sides by T2, effectively moving it over, and therefore getting our new formula. Okay, so let's plug in our values. So T1 is 295 Kelvin, and we are going to be multiplying that by 0.27 moles. And then we're going to divide that by 373 Kelvin. So now when that happens, what you're going to get is 295 times 0.27. Divide that number by 373, and we will get 0.21 moles of air is left in your jar. So we can make a new formula. And one thing to keep in mind too is if you remember that relationship here, being that they're in an inverse relationship, as temperature increases, moles should go down. And it did, which is great to see. Let's take a look at some different skills to master in this video. The next skill that's going to be very useful is how to find molar mass. Now, why is this something that's so important? Well, it helps you to be able to identify what gas you have. Meaning that you can't usually see the gases. So you can measure what they're all about, but you might not be able to just identify by looking around you, being like, oh, what gas is all around my head? You have to be able to do calculations to solve that. So in this problem, I have 2.787 gram sample of gas, and it's found to occupy a volume of 2.45 liters at 300 Kelvin and 1 atmosphere. We know that it's an elemental diatomic. Which one is it? Let's try to find out. So the first thing to think of is, well, when it comes to molar mass, which allows you to identify different substances, it's like the fingerprint for a lot of these molecules. It's one way to do that. So if I am to think of molar mass, right, that was grams over moles. Well, in this problem, I have my grams, right? So the way that we could essentially solve this is I know 2.787 grams on top, but I don't know my moles, which is N. So which formula can solve for moles? Well, this is where we'll use the ideal gas law. PV is equal to nRT. So being that is one thing you will notice is that this particular gas is at its current condition. Notice how there's no change involved. There's one volume, one pressure, one temperature. There's nothing else. So what we are going to end up doing is we are going to plug those values and solve for N. So we are going to rearrange the ideal gas law to get N by itself, and it's going to be pressure times volume divided by RT. So now what is R, in case you're wondering? That's just a constant value, and we're going to use it that we got to always make sure the units match what we are being given in the problem. So if they don't match, you're going to be really sad because you're not going to get the correct answer. So our pressure is 1 atmosphere, so that's going to go on top. We have our volume, which is 2.45 liters. And that's going to be divided by R, which is 0.08206. And that has a very complex set of units, liter, atmosphere, mole, Kelvin. And then that's going to be times temperature, which is 300 Kelvin. Okay. Now, when we're putting this in our calculators, you need to make sure that you are either using the fraction button to separate top and bottom, or use parentheses to separate them as well. So when we solve this, what we are going to get for the number of moles in the problem is a number around 0.0995 and then a bunch of decimals after that. And that's going to be units of moles. Now, does that match any molar mass? Well, we're not quite done, right? This number here you have to plug it in to the value, to the term that we had above. So if we take this value from before, so we are going to plug in our new number for N. So let's take that, and this will be grams over moles. And what, by putting these two things in your calculator, you're essentially simplifying it. So we do 2.787 divide by 0.0995, hit enter, and what you are going to get is a value close to 28 grams per mole. Now, which diatomic gas is it? Well, that's one thing you have to be able to remember is your diatomics. So if you're not sure about them, watch my video on the 7 diatomic gases because it's very important. So let's take a look at the list of diatomic. All right, if you remember my saying, have no fear of ice cold beer, you will never forget the 7 diatomics. So diatomic means 2. So being that we had a molar mass of 28 grams per mole, so if you divide that number by 2, you will get 14. So which element matches 14? Well, it's not hydrogen. Oh, nitrogen is 14. So 14 times 2 is 28. So our diatomic in this case is N2 gas. And that will be our answer for this problem. So sometimes you got to try to solve the mystery of what gas could be located in our sample. So we did it this time. Let's see if we can do it again in the future. All right, let's go on to the next problem. Okay, sometimes you will be given problems that involve diagrams and you have to be able to read what they're showing, especially when they show them in different atoms and molecules. And a lot of times they're referring to mixtures. So in this case, we have a mixture and it's sealed in this container that I have. Let's use a diagram to answer the following questions. So the first thing is you can see that in this purple vial here, I have 4 different gases. And the first thing I ask you is, okay, which gas has the highest partial pressure? Well, how can we do that? Well, this is where Dalton's law comes into play. Dalton's law had 2 different formulas that were really important, right? If you add up every pressure of each gas, you will get the total pressure. Same thing about moles. If you add the moles of each individual gas, being that they're indistinguishable particles from one another, you can't just count all the little air molecules around you and figure out what's nitrogen, oxygen. You just know what the pressure of your room is. You don't know what's each, but we can try to calculate it. We can approximate. So based on that, what that means is, well, whichever molecule has the most moles is exuding your highest pressure. So what we need to simply do in these types of problems is count what we have, right? As if you could count. So if we count the number of oxygens here, we're going to count each individual one of these little orbs here. So you see you have 1, 2, 3, 4, 5, 6, 7 red oxygens. So we are going to put a 7 here. For nitrogen or ammonia, we have 1, 2, 3, 4, 5. So we will put a 5 here. For HCl gas, we have 1, 2, 3, 4, 5 as well. And then neon, which is our purple, we have 1, 2, 3, and 4 in our molecule here, or in our different, our number of orbs that we have. All right, so which one is the highest? Well, being that oxygen has the most, this is having the most pressure out of all of them. So oxygen will be the most. The least amount of pressure would be neon because it has the lowest number of moles. So O2 is our answer. Now let's go on to another one. So if we assume each gas particle is 1 mole, what is the mole fraction of NH3? Well, okay. So mole fraction, what is that referring to? Well, if you look at this formula here, where partial pressure is equal to the total pressure times Ni over N total. What this part is in parentheses here, this is your mole fraction. Okay, so mole fraction. And usually the way that this guy is labeled is with the Greek letter chi to represent that you have a mole fraction. So if you ever see that, like that fancy looking X, that's telling you, hey, this is talking about the mole fraction. So the way it is if you remember before, I counted everything for us. So if we add up all those, remember each one is equal to 1. So we can get our total really easily. So if we do 7 plus 5, that's 12. 12 plus 5 is 17. 17 plus 4 is 21. So what we will put as our total, so we'll put that on the bottom. So we got 21 moles total of gas, and that's adding all the parts. And it's asking us what's the mole fraction of ammonia. So ammonia, we had 5 from earlier. So we are going to put that we had 5 moles of ammonia. So this is the literal definition of a mole fraction. So 5 over 21 in this case. Now, depending on who your teacher is and how the homeworks are, you either have to put it as a fraction, so 5 over 21, or you can put that in your calculator and simplify it. So if we do 5 divided by 21, we will get 0.238. With that value, you will notice that there is no units between it, being that moles technically cancels here because it's just a fraction. It's just a ratio of what we're trying to represent. Now, the last part is assume each gas represents 1 mole, like we did before. The total pressure of the container is 1.20 atmospheres. What is the partial pressure of HCl? So earlier I had that there was 5 moles of HCl, just to remind us of how many we had in our container. So how can we do this? So let's use this partial pressure equation that I've been kind of dancing around. So in this case, we want to know what the partial pressure of HCl is. So that will replace our I, because I is just an indice, it's just however you label it. In this case, we are labeling it as HCl. So we have our total pressure, which is 1.20 atmospheres. And then we're going to times that by our mole fraction. So that was 5 moles all over 21, which was the total number of moles. So that was all the little molecules that were in the container. So when we do 1.2 times 5 divided by 21, what we are going to get is 0.286 atmospheres of HCl. And ATM is atmospheres, not at the moment. It is atmospheres, just so everybody knows. All right, so that is our value here for this problem. Okay, so that wraps up our video on tips and tricks for solving gas laws, which, as you can see, gas laws can get very, very complicated and complex. So please refer to my other videos on how to practice these, which go through many examples through all the different gas laws and how to use them. And as I was saying earlier, the biggest thing, take home messages, is you need to stay organized, write down what all your values are, so that way you can match them to your different gas law formulas, which is always the most important part. Is that being that we do have all these gas laws, is you need to be able to read the word problem carefully and look for if there is change or if it's the current state. And that is what's most important. If you can notice that, the more you practice, the easier it will get. You can do this. I know you're capable of doing this. You're smart, you're intelligent, you can do it. So keep practicing. Let me know if you need any help in the comments or in class or in Discord or wherever, and let me know everything I can do to help you. And if you're someone just watching this for help, please hit that like and subscribe button. And if you see me on campus, say hi. All right, I'll see you all later. Bye now.